On our second video, we are picking up with how do we do atomic mass calculations? How do we find the atomic mass, which is a weighted average? First, let's take a look at weighted average problems in general. I like golf. I'm not very good at it. But let's say a golfer has 8 long golf tees, and those are the tees that they use when they're using a driver to tee off with. And they have 8 long tees, and the long tees have a mass of 1.25 grams. But also in the golf bag, a golfer has 2 shorter tees, which is the type of tees they might use if they're going to tee off with a wedge or a shorter club, 7-iron, 8-iron, something like that. The shorter tees only have a mass of 0.75 grams. What hole is the golfer on? In order to wait. No. What is the average mass of the golfer's tees? So they've got 8 tees at 1.25 and 2 tees at 0.75. Certainly the mass should be closer to the longer tee because they have more of them. We can't simply take the 1.25 and add it to the 0.75. If we take 1.25 and add it to 0.75, we get 2. 2 divided by 2 is 1. The average of a long tee and short tee, if we only had one of each, would be 1 gram. But we don't have one of each. The abundance of each of these, 8 long ones and 2 short ones, should affect the average, and it does. So how can we do the problem? One way is to take this route, method 1, and this isn't really how we do it in chem, but this does work. Method 2 is how we set it up in chem. We'll show you in just a second. Method 1, we could say there's 8 tees at 1.25 grams for a total of 10 grams. There's 2 tees at 0.75 grams for a total of 1.50 grams. Add those up. That's 11.5 grams. How many tees did we have? 10. 11.5 grams divided by 10, it's 1.15 grams per tee. That is one way to do it. In chemistry, we set them up a little differently, and this is how we would like you to set them up for this class. It's going to be the same idea. We know that 80% of them, there's 10 tees, 80% of them are 1.25 grams. So what we do is we convert the 80% back to decimal form. To get it in percent form, we multiplied something by 100. To get it out of decimal form, we would divide by 100. So we would take 80 divided by 100. Which is the same as sliding the decimal 2 to the left to get 0.8. 80%, which we now have converted to 0.8, are 1.25 grams. So 80% of the mass of the average is due to the ones that are 1.25 grams. 2 out of 10, or 20% of them, are the shorter tees. Again, we convert the 20% by dividing by 100, sliding the decimal 2 to the left to get 0.2. Those are 0.75 grams. So the shorter tee, the contribution of the shorter tee to the average mass is 20% of 0.75. The contribution of the longer tee is 80% of 1.25. What does that come out to? We would take 0.8 times 1.25, hit equals, then hit plus, parentheses, 0.2 times 0.75, hit parentheses on your calculator, equals. That would come out to 1.15. Now, since we only use 2 numbers as the smallest numbers used for the calculation, 3 out of 4 of the numbers only had 2 numbers. If one of the, what we do when we decide to round is we look to see which number was used in the calculation that had the fewest numbers. It was 2. So we would round 1.15 to 2 numbers. That would become 1.2. We can round up from that 5. 1.2's mass is much, much closer to the longer tee, which is 1.25 grams. So really, if we didn't round up, 1.15 grams is a lot closer to 1.25 grams than 0.75. Why? Because 80% of the tees were longer tees. So we set up the problems just like this. We take the percents that were given and we convert them back to decimal form by dividing by 100, which is the same as sliding the decimal 2 places to the left. We multiply that percent times the mass. Since we're working with atoms, we would be using the mass in AMUs. We would add that together. Above each of the expressions, we write what it is that's contributing to it. So you would say, which isotope was it? And when you do the problems in here, you must always show the entire setup. You don't just write the answer. You're going to write all of this out as we've done here. And when you do the calculation, you always use the numbers you are given. You save the rounding till you have the final answer. You never round a given answer. You use the numbers that you were given to do the calculation. All right, let's take a look at an example problem here. Find the atomic mass of carbon. In other words, what we're going to try to do is find out where this 12.01 came from. Where did they get the 12.01? If you remember, the isotopes that contributed to the mass were carbon-12 and carbon-13. Carbon-14 is so rare that it doesn't influence the mass whatsoever. The average mass, it's just so rare. Find the atomic mass of carbon. Well, we're going to take that 0.98 or 98.90, convert it back to decimal form by dividing by 100 or sliding the decimal 2 to the left. That's 0.9890, and we're going to multiply it by 12. Right down here, 0.9890, and we're going to multiply it by 12. How much of it was carbon-13? Carbon-13 is only 1.1%. Divide that by 100 or slide the decimal 2 to the left. What would you get? 0.0110, and it's 13.033 AMUs, or 0033 AMUs. There we go. How do we do this in our calculator? Parentheses, 0.9890 times 12.00, and when you plug the numbers in your calculator, you don't have to add those zeros on the end. But you do write them in the problem so that we know that those were measured spots. Parentheses plus, and then we can put this in your calculator using the parentheses, 0.011, you don't have to put that zero on the end, times 13.0033, parentheses, you would get 12.011. There they kept 1, 2, 3, 4, 5 numbers. We should have only kept 4 numbers there, so that would go to 12.01. which is what we would see in the box, 12.01. All right, that's example 1. Example 2. Example 3. How did they get oxygen's mass of 16 in the box? Oxygen's mass is 16. 99.757% of the oxygens are oxygen 16. Their mass is 15.994915. So we're going to take that mass, put it right in here. We're going to put the heading of oxygen 16 over it. We're going to convert this back to decimal form. We get 0.99757. Oxygen 17's mass also contributes it. Oxygen 17's mass is 16.999132. It's only 0.038% of that. We slide it 2 to the left and we would get 0.00038. Oxygen 18 is a little more abundant. It's 0.205%. Slide that 2 to the left, we would have 2 zeros now in front. 0.00205 times oxygen 18's mass. Oxygen's 18's mass is 17.99160. Boom, plug it in. Punch that all into your calculators, and you would get 15.9994053. How many numbers are we really allowed to keep? That's a good question. Apparently, we're rounding this to 16 because this one only has 2 numbers here, 0.038. You're like, what about that 0 leading off? Well, the 0 leading off a number doesn't count. It's the zeros on the end of a number that count. So we could round that to 16. But if we had more numbers, you'll see on the periodic table they would use more numbers. We would get 16 grams. Another example here is dealing with magnesium. There are 3 isotopes for magnesium. Magnesium 24 is 78.7%. 25 is 10.13%. Magnesium 26 is 11.17%. What's the atomic mass of magnesium if this is all their masses of the different isotopes? The first isotope is magnesium 24. I can write that above there. Convert that back to decimal form by sliding it 2 to the left or dividing by 100. There it is. What's the mass of magnesium 24? It's right there, 24.98584. or magnesium 24, excuse me, is 23,98504. Magnesium 24 is 24,985. There, that one goes there. What's its abundance? 10.13%. Slide the decimal 2 to the left to get it back in decimal form, which is the same as dividing by 100. It goes right there. Magnesium 26's mass is 25.98259. We write that right there. What percent of it is magnesium 26? 11.17%. Put it back in decimal form, divide by 100. That's sliding it 2 to the left. Plug that all into your calculator. You get this big long number here. We're allowed 4 numbers to work with on our final answer. So we look at this number right here, 2430. That 6 will round the 0 up to a 1. We now see where they get the 24.31. The next problem is slightly different. In the next problem, they're saying that there's 2 isotopes of carbon, carbon-63 and carbon-65. Or copper, excuse me, not carbon. Copper has 2 isotopes, copper-63 and copper-65. Copper-63's mass is 62.9298. And 69.09% of all copper is copper-63. The other isotope is copper-65. Well, if there's only 2 isotopes, and one of them is 69%, the other one, 69.09%, if we take 100 minus 69.09, we would get 30.91%. So the other one, with copper-65, would have to be 30.91%. What is the atomic mass of these isotopes? What is the atomic mass, the atomic mass between the isotopes? Copper's atomic mass is 63.546. So this time they told us the atomic mass, and they're wanting to know the mass of copper-65. So this time they told us the atomic mass, and they're wanting to know the mass of this isotope, copper-65. So we plug in copper-65, and that's what we're trying to find, this variable here. We know that 69.09% of it is copper-63. Divide that by 100 or slide the decimal 2 to the left, 69.09. What's the mass of copper-63? 62.9298. That goes in here. Do we know how much of what percent of the isotopes are copper-65? Absolutely. 30.91. Slide the decimal 2 to the left or divide by 100. Now we just have some algebra to do. We have 63.546 equals this stuff in parentheses plus this stuff in parentheses. We can resolve what's in here by just doing that calculation. 6909 times 62.9298. We get this right here. Write it out, don't round. Remember, round at the end of the problem. There, we're leaving this in parentheses because we don't know what this variable is. Now, how do I get 43.47819.882 off that side? Well, we could subtract that off both sides. That's what they're doing in this step right here. We're going to subtract both sides by 43.47, etc. 63.546 minus 43.47, etc. is 20.0678, etc. 43.47 minus 43.47 would just leave us. Those things would cancel out. That would leave us with 30.98 times whatever copper-65's mass is. Now, I can pull the parentheses out. How do I undo multiplication? I would divide both sides by 0.3091. If I divide this side by 0.3091, I divide this side by 0.3091. The 3091s cancel out. 20.067, etc. divided by 0.3091 is this number right here. The smallest number I had, or the smallest calculation numbers in a calculation was 4, so I round that to 64.92. The mass of copper-65 is 64.92. This is how we do the calculations. If they give you the atomic mass and other data, you can find the mass of one of the isotopes. Or if they give you the percent abundance and the mass of the isotopes, we showed you could calculate the atomic mass. Thanks for watching. If you have any questions, don't hesitate to ask.